All right, so we're starting our new chapter. It's Newton's laws. We'll see how far we get through the laws. And with Newton's laws, you have to be careful because most people learn Newton's laws in middle school or wherever, and people can say Newton's laws, but they can't really appreciate or actually apply them. And that's because of our conditions on Earth here that kind of screw up our idea of what's actually happening. So just keep that in mind. Just because you can't say it doesn't mean you actually put it into practice. So we're going to practice using Newton's laws this chapter. So let's look at this example here. If you have this ball or soccer ball and you were looking at it out in a field and all of a sudden it started moving, what would you think?
Wind.
Okay. So wind did what? Okay, can we use physics? Maybe force the ball to move, start moving. You mean it wasn't going to happen by itself? No. Okay. So, or since we're in Halloween, it was a ghost or something. Something made it move. All right? So, right, there had to be a reason for its moving. Now, what if the ball was rolling, if someone had kicked a soccer ball and it was rolling and the soccer ball came to a stop? Would that freak you out? Okay, most people know that you wouldn't say ghost in that case, all right? But you should treat those cases as identical. That, making something come to a stop. If something comes to a stop all by itself, it should be just as freaky as if it started moving all by itself. So there must have been a force to make it stop. Now your choices are again ghost or wind or friction, which is a force. And because friction's always there, we always think things will always come to a stop, but yet we always need a force to make something move. And that is not correct. That is not what Newton said, nor one of his predecessors, Galileo. So, first of all, Galileo was first to start to study motion and what was happening. And he believed Copernicus, which was his mentor in a sense, and Copernicus' theory that the Earth and other planets moved around the sun. That was a big, big deal. It was heresy against the church because the Earth was supposed to be stationary and the center of the universe. And all of a sudden someone saying, no, the Earth is moving and we're not in the middle. And so that kind of went against people's beliefs. And so that was a big deal. And then Galileo got rid of the idea that a force is necessary to keep an object moving. All right? A force is not necessary to keep an object moving. Now that we're mentioning the word force, that's kind of new for us, we need to have some words to describe what a force is. And I bet you did do this in middle school, at least this far. Okay, I heard any push or... And that really does work, okay? So if you can interchange, if you're using the word force, you can always interchange the word push or pull in that. All right, friction is a force. It's any force that acts between materials that touch as they move past. So if you have two materials touching and sandwiching, and they're rubbing against each other, that is causing some friction. And it's going to be against. It is in the opposite direction of the motion. Even very smooth objects at a molecular level are bumpy, and you can think of a bumpy surface riding on another bumpy surface, and it's going along. And then we can kind of think if we obviously make it smoother, things are better. But it also is somewhat the attractions between the molecules, between the different substances. So it isn't just how smooth you make it. We're going to do some labs later. You're going to discover how much force it takes when we drag objects across each other. And you're going to see some things like aluminum on aluminum is not the same thing as maybe steel on steel or some other substance you might have. Ice on ice, not going to be the same. All right. Okay. So even smooth objects have friction. All right, so that kind of messes our little world, all right? So Galileo, not having a lot of tools, did some mind experiments and thought about this. And he said, if there is a lot of friction, a rolling ball doesn't go very far. So if you roll a ball, let's say on carpet, right? It's going to peter out pretty quick. It's not going to roll real far. Think about if our halls here were carpeted with shag carpeting, right? And you rolled something on, it's not going to go. Okay, it'd be really gross, even grosser than upstairs is now. Okay, right? If there is little friction, so let's say you have our tile in the hall and you roll a ball, all right? As long as when our halls aren't straight, but imagine if we had straight halls and the ball could actually maybe go for a while. All right, so it goes further, right? Because there's less friction. So then Galileo said, well, what if I could eliminate all friction? What would happen to the rolling ball? Okay, it would go forever. Because there wouldn't be friction to stop it. So you really have to keep this in mind. A ball doesn't need something, a force or a push to keep it going. It just needs something to not stop it. All right? And that's a lot different. We don't have this world of no friction, so it's nothing we see in a daily basis. You might see it in some computer games if you play some space games, all right? The old game called Asteroids. All right, if you've ever played that, if you hit your little rocket, your rocket will start going and going forever. You get some speed built up, and it's just looping through the screen over and over until you make your rocket kind of push back the other way. So it's not going to ever slow down, all right? Here's another experiment that Galileo thought of, and he said, well, if I roll a ball down a hill, right, what's gravity going to do? Gravity's going to make it go faster and faster, right? If I roll a ball up a hill, what's going to happen? It's going to go slower and slower. So do you see how he doesn't need any great sand timers or anything to do this? All right. And then he reasoned, okay, this goes faster, this goes slower. So if I have no slope, what should happen? Unchanged, right? So the speed, right, remains constant. Okay? So once again, we do not need something to keep something moving. Okay? Then we have this concept called inertia. Okay? A lot of people struggle with this too. We can again say the word, you have a little bit of understanding of it, but people still use it improperly. Okay? Inertia is the property of a body to resist change in its state of motion. Change in its state of motion. A lot of people think inertia is only that things don't want to move. Okay? Because students like that. Right? You right now feel like you have a lot of inertia, and right, you're at rest and you would like to remain at rest, right? It's kind of hard to get you moving. That's true. All right? But it's the opposite is going to be true as well. If it's hard to make something start to move, it's equally hard to make it stop moving. So inertia is just changing. It doesn't want to change its state of motion. That means it could have been moving or it could have been at rest. People only want to think about the rest condition, but it also could be at moving. Okay? Well, Galileo then basically Newton took Galileo's ideas and solidified it and wrote it into some laws. Okay? So Galileo was born near the year of Galileo's death. And Newton was a sickly boy, and people thought he was going to amount to much. But because he was sickly, I think he spent a lot of time thinking. In fact, he says why he was able to do so much in his very short life, he lived only into his early 20s, is that he said he thought long and hard about things. Okay? So I always take that as, not fun. Okay? Right? But if you want to understand these principles, you have to think long and hard. So Newton's first law of motion is also called the law of inertia. And he just basically restated these ideas that Galileo came up with. And that is, every object continues in a state of rest. Everyone's good about that one. Or uniform speed in a straight line unless acted on by a non-zero net force. There's a lot there. So everything's going to either going to be at rest or it could be moving. But if it is moving, it's not changing its speed and it's also not changing its direction. Unless it's basically, this says non-zero net force means there must be some overall force, okay, that doesn't cancel out. All right, and if there is a force, then then it could change. It could, if there was a force, it could change its rest. If there was a force, it might not be moving in a straight line. Okay. Paraphrasing. Things tend to keep doing what they're doing. You guys have a lot of inertia, right? You just want to keep doing what you're doing, whether it's right or wrong, right? And you have to be forced to change your ways, right? And the same thing with all objects. And the classic example is you could pull like a tablecloth from under some dishes. And how that would work, right, is that your dishes have, and you shouldn't use something too light. Paper plates aren't going to work out too well. You need something that has a little more inertia. And if you pull really fast, those objects on the table don't want to change their state. Okay? All right. All right. Again, objects in motion, moving objects tend to move in a straight line indefinitely. Okay? If there are no forces. So many people think that there must be a force to keep something moving. Okay? This is about as close as we can get on Earth. If we smack a hockey puck on ice, right? It'll keep going across the ice. Are you going to see it going across the ice and start to change direction and curve around a little bit all by itself? No. All right? And when is it going to stop? When it hits the wall, right? Something has to force it to stop. Either a wall or there's a person, right? Okay? A hockey stick, something to stop it. Okay? Because that's just our close situation of no friction. A rock in space will continue in a straight line until gravity of some planet might suck it in. Okay? A moving train, all right, may have a lot of inertia, and we'll talk about why in a minute. And it will want to move straight. Okay? Do you ever look at railroad tracks? Are they really curvy? No. That's trouble. In fact, whenever there's a problem with a train, it's usually in a curve. All right? Because the train wants to keep going in a straight line unless it's forced, and you better have it set up that you can force it to change direction. Okay? All right. Okay. Somehow this relates to mass. Let's see. Here's another little experiment we don't have to do because you just think about it. I actually used to do this until I kicked someone in the face with a can. So I just kind of stopped at that point. All right. Imagine you have an empty pop can. It was on the ground and you just, swung your foot back and gave it a big kick, right? It'll go flying, right? Okay, so, all right, goes fast and flies through the air. What if someone filled that can full of sand before you kicked it? Okay? All right? What are you going to... Okay, it's going to go slower, right? All right? And you're going to know, right? First of all, it's not going to go as fast, and you're going to feel it, right? You're going to feel... Isn't it going to resist moving more than the empty can? Okay. All right, what if I filled it with lead, like my lead brick here? How's that going to work out? All right? Okay. All right. We're not going to drink it. Okay. Only in Flint. Okay. All right. So this, what's going to happen, right?
Your foot will break.
Okay, your foot will break. All right. And it hardly moves, right? Maybe you'll tip it over. All right. So do you think we're figuring out what inertia has to do with? Okay, so the more mass, the more inertia. And in fact, you can interchange those words. If you're not sure if you're using the word inertia correct, just replace the word with mass. Okay? You should be able to. All right? If you can't, you're not really using inertia right. I have a lot of people, this is one of my pet peeves, will be doing something, and they'll be talking, maybe it's about a train or something that has a lot of mass, right? And they say a train takes a while to get going until it overcomes its inertia. I have a problem with that. Because that's like saying overcomes its mass. You mean like it doesn't have it anymore? Like, right? No. Is it like fear? Like it overcame its fear and now, okay. Did it overcome its resistance to change its motion? Once the train is moving, how easy is it to stop? Not. So it still has its inertia. It didn't overcome it. There is no overcoming inertia unless you chopped part of it off and got rid of mass. Okay? Then you could overcome something. Okay? So don't use that. Don't use that phrasing because it's not really correct. All right? So if something has a lot of mass, you're kind of out of luck. Right? You're kind of out of luck if you want to change its motion. Right? Now, if you don't want to change its motion, all right. Yeah? Okay? Then you're good. All right. So since it's mass, all right, we know our unit for inertia, right? It's going to be the kilogram. Okay? So if an object has a large mass, I shouldn't have to say this, it may not have a large volume, like right here, right? My lead, it just could be really dense as long as it has a lot of mass, right? So you can't just use the word big. And something is big, so it has a lot of inertia, right? You need to make sure you realize it's a lot of mass. Okay. Now that we're talking about mass, we also have to relate, and we're talking about forces, we have to realize that mass and weight are not the same thing. Sometimes we can use them interchangeably on Earth because they are relative to each other. One goes the proportional, if one goes up, the other goes up. But we have to be careful. Okay? Mass is the amount of what you learn in chemistry. Stuff. The amount of matter. Okay? This means how many atoms are there. And then once you have those atoms, like this is a lot of stuff, not just because there's a lot of atoms here, but every atom has a lot of protons and neutrons in it that add to the mass of each atom, and they're close together, so we have a lot of mass. Okay? All right. Depends how many and what types of atoms are in it. It's a property of the object itself. Okay? And so that's never going to change. Wherever I have this lead brick, it's going to have the same mass and going to have the same inertia. Keep that in mind. It doesn't matter where I transport this. Now, pounds are a unit of weight. It's a force. It's the pull of gravity acting on an object. Okay? Kilograms are a unit of mass inertia, and pounds are a unit of weight. How much a planet or a large mass is going to be pulling on that object. Okay? Do you know how you feel weight? How you feel weight is you go like this. Oh, because I'm pulling it against gravity. Isn't gravity down? Yeah. Okay, so I'm seeing how easy it is to lift up. Okay? Do you know how I can't do this very well here. Do you know how you feel inertia?
Pushing it.
This. And you go, what's the difference, Ms. Jones? Okay. Because I'm not lifting it now, but I have to start it and stop it. Okay? How about this? What if I put this on wheels and I give it a push to see? That would be feeling for its mass. Okay? And then if I, again, lift it up, I could feel its weight. Now, imagine if you were on the moon, where gravity is about 1/6 that on Earth. Do you realize, so how would those things help you in that case, right? So if you were on the moon and I went like this, wouldn't this be much easier? Because the moon isn't pulling as hard, and I could pull back much easier on it. Okay? How about this? Same. Okay? All right? So if I were to roll this, okay, or if I were to throw it at someone on the moon, okay, is it going to be, 6 times easier because the gravity's 6 times less to catch it and to slow it down? No. All right? Not at all. Could I lob it further? Yes, because in our formulas, gravity's in our formula, and it would take longer for it to fall down on the moon. But could I pitch it faster? No. Because I can't change its inertia any better. It still has the same mass. All right? So those are things to contemplate. Horizontal things, which has nothing to do with gravity, are not any easier if you get rid of gravity. Okay? All right? Think about floating objects in this way. So if you make something float on, let's say, water, then, of course, like, they're easier to lift. You could put your hands under a large ship and go, look, I'm holding it up. Yeah? Go, look how strong I am. Okay? But what if you try to push it out of the way? Right? The Disney cruise ship. How's that going to work out? You swim up to it. It's floating. How's it going to work if you go to try to shove it? You're going to move. All right? Because you know why? You don't have a lot of inertia. You're easy to change your state. That giant ship still has mass just because it's floating. Floating just means you can put your hands under it and it's going to be okay. All right? Doesn't mean you can make it move horizontally any easier. Okay? So keep that in mind. All right. So let's look at this. 1 kilogram mass on Earth weighs, if you want a number, on Earth, 2.2 pounds. That conversion doesn't work anywhere else. So this is the kind of conversion people always want to know. If we have our international students, they only know their mass in kilograms, and we only know it in pounds. So basically, you double it and add 10%. Okay? All right? So if it's 50 kilograms, double it 100, add 10%, 110. Okay? That's the easy, quick math. All right. On the moon, not so, because, again, gravity is less, and your answer ends up being 0.364 pounds. Awesome. Okay? All right? Yes, you can lose weight by going to the moon. Unfortunately, you're just as hard to move. All right. 1 kilogram mass in deep space weighs, we're going to assume in deep space where there aren't things that there is no gravity, and it would be 0. And what about the mass? What about the mass? In anywhere, it's always going to be the same. Okay. All right, so that's Newton's first law. So we're moving on to his second law. All right. And Newton's second law says it's just continuation of the idea of the first. If an object is at rest or constant velocity with no force on it, let's talk about something called a net force. Okay? What happens when you do have a force? Okay? And Newton said this: the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to the object's mass. The direction of the acceleration is in the direction of the net force acting on the object. What? Okay. So we see this word acceleration, which we know, okay? And we see that it's proportional to something called net force. Net force, let's talk about this. Some people don't know what that word net means, okay? We're not talking about something to catch a butterfly, all right? So net as opposed to gross. And some people understand this if you ever get a paycheck, okay? If you get a paycheck, you have net pay and then you have gross pay. Gross pay is what you were told you were going to get paid, like your hourly pay. Yeah. And your net pay is when you look at the check and you go, what? This is all I have? And that's because your net pay is when you take away all the things that subtract out. Okay? It's what you have left over. So when we talk about forces, sometimes there's more. You might be pushing, but something else might be pushing back, like friction or gravity or something else that's also interfering. So we can't just look at one force. We have to look at, okay, how many forces are on here? Vectors, because they have direction. Let's cancel out. Let's see what's left over. Okay? So net force is the leftover force. Okay? All right? And it could be nothing. And if it's nothing, you're not going to get any acceleration. Okay? And the last thing is the direction of the acceleration is the direction of the net force. If you could draw a force arrow of what's left over, that is the direction of your acceleration arrow. Okay. All right. So what is the formula here? All these words, we like to make into a formula. So A is, I'm going to put a fraction line, it's proportional to the net force. So A goes as F net, so we're going to write it like that. Okay? I don't want to write F and just an N for net. Yeah. That's it. One second. I'm just going to give you a second one, and you just do the backside and put them together. All right. So we have A is proportional to F net, and what about the bottom? It's inversely proportional to. So if it's something's inversely, doesn't that part go on the bottom? So this is the way that Newton said it. But normally, we switch it around. And so how is it more commonly written? Have you ever seen this? What do we normally say? F equals ma. All right, but please don't just write F. You can't just read a story problem and just see a force and go, oh, I'm going to put that in for there. Because you've got to make sure it's the net force, the sum of all the forces. In fact, many times, instead of writing like this, you know what else you could do? I could get rid of this and do it like you would in math class. If I said sum of all the forces, does anyone know a Greek symbol for sum of? You could do that. Is that PTSD? Yeah. Okay. Okay. Put it back then. It's okay.
So convenient on your calculator.
Okay. All right. All right. So the SI unit for force is the Newton. Okay? Since F equals ma, okay, pay attention. We're going to get some base units. What is a Newton made out of? So force, this is going to be newtons. So what is it made out of? So we're going to take a mass. What are the units for mass? Kilograms. And we're going to end up timesing it by the units for acceleration, which are all of that. Blech. There you go. That's what a Newton is. So you can write 1 Newton or you can write 1 kilogram meter per second squared. Okay. The CGS, do you remember there's something called the CGS, the centimeter gram second system? And I'm mentioning this because if you go into engineering and you got some old school teachers, you might see a unit called a dyne. And a dyne is made out of what if it comes from the CGS? Instead of kilogram, gram. A centimeter is not an equivalent to a gram. Okay. All right. And then instead of meters per second squared, it would be centimeters per second squared. Is this a big unit or a little unit? Baby. Real baby. How baby? Do you realize that this is 1,000 times smaller? And then this is... So how much smaller is 1 dyne compared to a Newton?
1,000 times more.
1,000 times 100 more. Wow, it's amazing. There are 100,000 dynes in 1 Newton. It's teeny, and I hate dynes, but I'm just showing you. Okay, the British unit is the pound. This is fun. What are the base units for the pound? So the American. What am I going to put here? I can't put a pound for a pound. Yeah? No. So, no, this is later. That doesn't help us. I need the parts, the base units. I told you guys once, a long time ago.
Mass is going to be pounds. Slug.
Slug?
per
foot per second squared.
Isn't that awesome? It's like I just made that up, right? I'm just
So
fooling.
it's slug foot per second squared, or is it slug times foot per second squared?
Well, all of these are, slug foot. All right. And then if you want to convert, 1 pound is 4.45 newtons. This is a conversion factor between 2 units of measurement. This is 3 significant digits. Okay? Both are force. Pound is force, Newton is force. All right, how much force is necessary to accelerate 160? I'm trying to make 3 sig figs out of that. Hockey puck at 64 meters per second squared. All right, so what are we going to do? Okay, so now what? Easy. But we got to use the right units. I want newtons, of course. I want no slugs. All right. So what am I going to do? What's my mass? 1,000 grams per kilogram, right? Times 64 meters per second squared. And if you do that, you would get 10.2 kilograms meters per second squared, better known as Newton. Okay? That's the net force necessary. Okay? How much will that amount of force accelerate a 1,400 kilogram car? So that force could really make that hockey puck move. Okay? How much can it make a car move? All right. So we're going to do this again. F net equals ma. But now this is 1,400, and I know my force that I'm going to use. And so what's my acceleration going to be? Real fast? When I divide by a real big number? Okay. 3. I should have another, and I don't. Oopsie. Oh, there's only 2. Yay! All right. And what's my unit now? So we, again, got rid of the kilograms out of our newtons, so we're back to meters per second squared. All right. So very low acceleration, because this is what Newton said, right? Inversely proportional to mass. If something has a lot of mass, it's not going to have a lot of acceleration unless you give it a lot of force. Okay? It has a lot of inertia. It doesn't want to change. We can see that. Okay. Let's talk a little bit more about weight. Weight is the force of gravity on an object. All right? And since it's a force, we can say F equals ma. And if I want to specify, instead of just any old force, I'm going to put F sub g for force of gravity, which represents weight. All right? And what is it going to be? Instead of ma, it's going to be m times g times Earth's gravity, acceleration due to gravity. All right? Right? Where our g, we're going to make 9.80 meters per second squared. Oh, yep. Let's do that because which way is weight? It's a force downward. Yep, thanks for correcting. Okay. All right. What is the weight of your 2-kilogram textbook that you're carrying every day because you love physics? All right. So we're going to take 2.0 kilograms and we're going to times it by negative 9.80 meters per second squared. And if you do that, you get 19.6. Only got 2 sig figs. So 20. I hate when it's like that. I'm putting the decimal. I know it's a cheat. Okay. And our units. Whoops. And it's negative. Okay. So 20 newtons downward. Okay? So how do you keep that from accelerating downward? Oh, you have to, right? You have to push upward. Because since you don't want it to accelerate, don't you need the F net to be 0? So you have to do that. This is a little bit more, this is very general, okay? Very general, not with sig figs. This is if you just want to think, this is a regular physics statement here, or physics for dummies, all right? If you want to be nice and general, to find the weight of a guy named Ben, do kilograms times the number 10. Okay, because 9.8 is about 10. All right. All right. Newton's third law, which is, again, something that people can say very easily, but the ramifications of it end up being complicated and strange how things work out with it. Okay. Newton's third law, we know a force is a push or pull, but we're going to say now Newton said it's a little more. It's an interaction. You can't have one. You can't have one force ever. Automatically, they come in pairs. Automatically, they come in pairs. You can't have one. Okay, let's try this. Here's an example. A hammer hits a nail. So here we have, got a little nail. Okay. All right, so here we got a hammer. Oh, I don't want to see John's hand. He's going to put a butterfly with it. It's going to be a problem. All right. So, all right. We got a hammer hitting a nail. All right. And so what can we say? We say the hammer exerts what? A force on what? Nail. Okay. There's the statement. What's the evidence? What happens? Okay, the nail moves. It changes its state. Didn't we say if we have a force, we can change something's state of motion? So the nail, doesn't it accelerate? Didn't it move? Didn't it change its state? Right? Right? It moves when it wasn't moving before? Okay. All right. What happens to the hammer? Does it keep going forever? Oh, why does it go forever? Oh, so wasn't the hammer, if not slowed or stopped, or what else could it do? Okay, it could bounce back, right? Could come back. All of these things, aren't these a change in state as well? So if the hammer changed state, so first of all, I'm going to put a force on that nail. This is the force of the hammer on the nail. So blank exerts a nail exerts a force on the hammer. How big? Little?
Equal.
Little because it's a little nail? Oh, I hear some experience. Someone said equal and opposite. If you're going to draw an arrow, you better make it equal in length and opposite in direction. So this is the force of the nail on the hammer. People don't like this equal. And they go, but the nail's little. I know. But you say, but the hammer, it didn't move nearly as much as I could make that nail move. I know, because they don't have the same mass. But it doesn't mean the forces are not the same. Okay? All right. So what's Newton's third law? Again, you've heard this before. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. People, again, don't take this properly to heart. All forces exist as action-reaction pairs. And please, 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 please follow. I can't make enough stars because this is what people screw up, this general format. A forces B in some direction, and the reaction is B forces A in the opposite direction. A lot of people get in a mix-up, and they will have A on B, and then the reaction is A on B again. Or it's A on B, and then B on C. Does that sound like an action-reaction pair? No, that's a triplet. That doesn't work. if then you know you've missed the pairs and you haven't paired things up properly. Okay. All right. Let's figure out why you can walk. Okay? I'm going to ruin your world. Now even when you're walking down the hall, you're going to think about physics. All right. Here you go. Here's your little foot. All right. And your little... There your little... Okay. Okay. You got big socks on? All right. Okay. There you go. All right. How come you can walk? Why are you moving forward? Because you're pushing. Okay. So what can your foot do? Your foot does what? Pushes what? What can that do? That only thing that can do is make the ground move. If you say, I moved forward because I pushed on the ground, that is really bad physics. Because that is a force like this. Can that force make something change its state in the other direction?
Yes.
Because we said, Newton's second law said the force and the acceleration are in the same direction. So this force can only make something move that way. That force cannot make you move forward. So I need to put a comma, and then we say, I already heard it, we can say A on B, ground pushes foot. Oh, I should have had a direction. Oh, bad teacher. And then I can say forward. Okay. And then people go, Miss Jones, inanimate objects don't have hands or feet and can't kick and struggle. All right? This is just craziness. What you have to think about things are at a molecular level, that things are made out of molecules, and kind of think like you pushed molecules closer together in your push back, and they're responding. Like when you sit on a couch and you squeeze the cushion, and the cushion is pushing back on you. Think of it like springs, okay? And you kind of squeeze things together, and they're going to want to push back, okay? An ice skater pushes against a rail. And so what happens to the ice skater? Don't they go backwards? So are they going backwards because they pushed against the rail? We can say the rail pushes skater right backwards. Okay. How about a rocket? Do you know for the longest time we thought rockets couldn't fly in space? Especially if they look like this. All right. There we go. All right. We're in space. It's in space. I didn't launch it now. This is later. Okay? All right. All right. So what if it wants to move in space? It can't be like a bird and flap its wings, okay? Or have a propeller. Why doesn't a propeller work? There's nothing to push against. You go, and this is what early people thought. We can't do anything in space. There's nothing to push against. With a propeller, you can push back, and then the air pushes you forward, right? And in fact, if air gets thin, so helicopters don't work. You can't rescue people off of the top of Mount Everest very easily because the air is too thin. The air is too thin. There's nothing for those helicopter blades to push down on so the helicopter blades can create lift and push up. So in space, there is no air at all. You can't flap anything. It's not going to work out. So they thought, that's not going to work out. So we have to do something else. So what do?
You push super hard.
What do you have here? Okay. So we do this. So we can say, oh my. All right. So we can have exploding gases, right? Isn't that what's happening in a rocket? Okay. And what happens? They're pushed back. And in fact, that's why this is this shape. We don't just explode things in a circular like in all directions. That won't do anything. You don't just have explosion, a circular explosion. You make it go one way. So exploding gases pushed backwards. And what's that going to do then? So then we can say A on B. So we can say now, right? I should really say, use the word rocket, right? The rocket has exploding gases and push. So now we can say the exploding gases can push the rocket forward. So the rocket is pushing the gases out, and the gases is going to push the rocket forward. Okay? Please, again, keep in mind, a force exerted by a body does not influence that body. You can't make yourself go. Okay? You can't make yourself go. You could push on something else. The only thing you could do is make that other thing move. Okay? All right? Yes? All right. So if you can't put a force on something, then something else also can't put a force on you. That's interesting, too. Okay? All right. So again, how can an inanimate object exert a force? Again, think about things being elastic. How much time do I have left when we get out? Oh, we're good. Oh, this is good. We'll get right into this discussion. This is going to throw people off. All right. Okay, we got a box on a table. We do a lot of things with boxes in physics. You know why? Because they're so easy to draw. All right, we can make something more complicated, but all right. Even John can draw a box. Okay. All right. Okay, we got a box sitting. Look what I said. On the table at rest. So we know Newton said lots of things already. If the box is at rest, what's my acceleration? This is not accelerating. So what's the net force on it?
0.
Has to be. That's what Newton said. But we know there's forces on the box. I already heard James say, I know there's some 9.8 there somewhere. And we know there's a force on it. But what force is that?
Gravity.
Okay, the force of gravity. So we know there is weight here. I'm going to, in fact, draw it. Now, when we draw what's called a free body diagram, where we show all the arrows and all the forces acting on one object. We don't do it on all objects because it would go forever if you haven't figured that out, because everything is pushing everything else. But we're going to focus on this box only. And how do we draw the force of gravity? Force of gravity pulls from the center of a mass. Okay? And so we're going to assume this is symmetrical and uniformly, mass is displaced. So I'm going to draw it from the center. It is the only force that we have that's drawn from the center of an object. Well, maybe you could draw magnetism that way. But all our other forces are what I call touchy forces, contact forces. But this one is not, right? The Earth has no contact with it, and yet it can pull on it. It's kind of magical, is it not? Okay? Yes?
Do we draw it from the center of gravity or center of mass?
Smart guy. The center of gravity. All right. Center of gravity and center of mass are synonymous if the object is not so big that gravity pulls differently on one part than the other part. You would need a mountain to have a possibly where the center of mass and center of gravity are not the same thing. We're going to do it from the middle. Okay. That's representing my weight, right? Okay. Can that be the only force?
No.
No, because is that equal and does this add to 0? So there must be another force to do what? To cancel the force of gravity. And that force is the normal force. Now, that normal does not mean like, hey, it's Joe Common. That word normal, okay, all right, means perpendicular in math class. Blah, I know. Okay. Oh, it means perpendicular. Okay, that's supposed to be my perpendicular symbol. Okay. A normal force is a contact force. These are perpendicular to the common surface. Okay. So I'm going to draw that in. I'm going to make a different color. And it's where they touch. Who's providing this force? The table. How big should I draw this arrow? Same length. It's kind of hard when they don't leave the same place. All right, so I'm going to label this F big N for normal. That's why I said net, make net, NET, or a summation symbol. Okay. Asterisks are FG and the normal force action-reaction pairs. This is a very, very important big concept. Are they action-reaction pairs? What do we say about action-reaction pairs? Action-reaction pairs is A on B and B on A. Yeah? Okay? They look equal and opposite. Let's try. Let's try. Okay, let's do the action first. And what was our action here? We said, let's do this. Okay, so, well, let's do the table first. Let me just do the table first. So what do we can say table does what? Pulls?
Pushes.
Oh, pushes. Pushes, which way? Up on box. Okay. All right. What is the reaction to that? You go, what happened to force of gravity? Oh. Was force of gravity and the normal force and action-reaction pair? Yes. No, this is the pair. You know why? Let's try to write what the force of... Can you write a statement just like we did for the force of gravity? You need two objects. So can you name those objects? We know there's the box. What else is there? Earth. Uh-oh. Now we have Earth, box, and table. What did I say about a threesome? No. Okay, wait. We have to first do the first one. What's force of gravity? Force of gravity is what? Pulling on what? Earth, pull, box. Which way? Down. Okay. It's like we're cavemen in how we say this, yeah? All right, I'm going to relate. I could teach this to a cave. Oh, now people are so sad about this next one. What's the reaction to that? Box?
Box pull Earth up.
It has to be. And people go, that's just stupid, Miss Jones. All right. All right. Here we have Mr. Earth.
Mr. Earth.
Mrs. Earth?
That's a very large table.
That is a better table.
How come no one said I drew a really good circle? Okay. All right, now let me fix the box, because someone's going to say it's levitating too. Okay.
Those things are bigger than mountains, so they're center of mass.
Oh, yeah, okay. All right. -5. Okay. All right. So, I'm going to do this. I'm going to draw an arrow of the Earth, just the same. That's my FG, right? This is the Earth pulling on the box. Now I'm going to make the box pull on the Earth from the center, right? How big should I draw that arrow? Oh, good job. Same length. Okay. Now. Okay.
Using a ruler.
You guys suck. All right.
That's a really good circle.
Okay. Thank you. All right. Okay. So, but you're telling me that the Earth is falling towards the box? And I'm going to say yes, it's accelerating. How much is it accelerating? Didn't Newton say F equals ma, though? How big is the m of the Earth? Okay, do you remember how we did that with the car, and the car was 1,400? It was nothing like compared to the puck, hockey puck. What do you think now? There's my m. So what kind of A is my Earth going to have? Okay. Okay. While the other one for the same force, which by the way wasn't too big, right, was a little m and a substantial A. Okay, because gravity's pretty substantial, 9.8. A.
Oh, for the second one. Oh, no, that one. Is that for gravity?
Yeah. Gravity's an acceleration. So the reason the Earth, if you have two objects like that, two objects are pulled towards each other. That's a later satellite chapter. The closer they are, they're more equal. Obviously, their accelerations towards each other, right? But this exists. This is real. It's just not significant, right? That's like, kicking the tire of a giant truck, right? It's just not really going to make any difference. Okay. All right. That's where we're ending. All right. And then we'll continue our discussion, and we have an inertia lab.